All right, hey YouTube, welcome back to the VSL Aviation YouTube channel. My name is Seth and I'm on episode 3 of the engine series. So we did episodes 1 and 2. Episode 1 was on the crankshaft and the camshaft. Episode 2 was on the case and all of its components. And episode 3 is going to be all about the piston. So this is a really important episode because the piston is really where all the magic happens of the engine. So far, all we've talked about with the crank, the cam, and the case are those are the components that actually transfer the energy that the cylinders create to the propeller and hold everything together. The cylinders themselves, though, this is the actual engine. In fact, it wouldn't be incorrect to think about your engine as basically each cylinder is a tiny little engine connected to a common crankshaft. So your engine actually has 4 tiny engines because this is where all the power is being created. So we've gotten this cylinder taken apart basically completely. So you probably recognize the look of this, right? You've seen these little cooling fins when you do your pre-flight inspection. You probably know that that's their purpose, is they increase the surface area of the cylinder and they act as a heat exchanger. So they take the hot cylinder and transfer that heat to the air that's coming in the cowling. Now inside the cylinder, you can see that it's pretty shiny and there's some holes in the bottom of that cylinder. So let's talk about what each of those holes is for. So first off, you have a big valve right there. That's a hole and there's a valve on the other side. That's our exhaust valve. So that would open and close to allow the exhaust to escape. And when the engine is, when we're in the squeeze mode of the cycle, that valve would close and it would allow compression to take place there. This valve over here, this is our intake valve. The intake valve is what allows air to come inside the engine. And remember, in a carbureted engine, that would be a fuel-air mixture. So that's not just going to be air, it's going to be air that's been mixed with fuel at our carburetor. The other 2 holes, those holes are where the spark plugs go. So the spark plugs would go inside this part of the cylinder, and the head of the spark plug that has the sparky part on it would enter in right there, and that's where the spark occurs. So when the compression stroke happens, the squeeze happens, then the bang is activated when those spark plugs ignite. As the spark plugs ignite, an explosion takes place, basically combustion takes place, and it powers the piston down, which is connected to our crank. So let's talk about the piston, because this is just the jug. This is just half of our piston here. The jug is where the piston goes. The actual piston, on the other hand, is this guy right here. So this is our piston. So the piston serves several purposes. The main thing is it allows, it's kind of the plunger in the syringe. Everybody's seen a medical syringe or gotten a shot. You've got the little plunger with the rubber gasket, and as the nurse or doctor pushes the plunger in, it forces the fluid that's in the plunger out the end of the needle. So this is kind of our plunger. It goes inside the cylinder and causes compression to happen. So let's talk about the plunger analogy more with the syringe. Now that plunger has a little rubber gasket to help it seal. You could imagine if you took that rubber gasket out, the seal wouldn't happen, and as you push, you would get fluid that bypasses the plunger. It just wouldn't work very well. Well, obviously we can't put rubber gasket around this thing to cause compression because the rubber would melt as soon as we started the engine. If we put metal on and we make this cylinder fit perfectly, or we make this piston fit perfectly inside this cylinder, there would be so much metal on metal contact that we couldn't keep it cool. And that would be a problem because after probably 5 or 6 revolutions, this would build up so much heat that it would start to deform and it would fail. So the way we fix that is with these tiny rings. So these rings are a really important part of our cylinder assembly. So right now I've got the rings lined up so that their gaps are right there in the same spot. And I'm moving them back and forth. You can see how there's quite a bit of spring force in that ring assembly. And we have 3 rings. The top 2 rings, these are compression rings. So they're acting as the same purpose, they're serving the same purpose as that rubber gasket on a hospital syringe. The reason there's gaps in them is because we need to have them have a spring force, because first of all, this is all heating up to about 350 to 400 degrees. So when it's a cold engine versus a hot engine, expansion is going to take place. So a cold engine is going to be smaller than a hot engine, so as it heats up, it's going to expand. So that's why we need these to have the ability to spring back and forth and soak up that expansion and contraction that naturally happens with our engine. The reason we have 2 is if these 2 gaps were to line up, we would lose compression through that gap. You can imagine the cylinder walls encircling this. The gas would escape through these 2 rings. So what we do is we create 2 rings and we rotate them opposite of one another. So now the gaps are at opposite sides and they help build compression. So now the gas can't escape. It has 2 places to escape from, and it can't make that escape happen. Now this gap is pretty exaggerated because these aren't installed, so the gap would be smaller there. And then the clearance of the actual piston head and the cylinder wall is pretty narrow as well. So our cylinders aren't airtight when they're making compression. There is a little bit of leak by, but it's allowable and we know about it, and that's one of the things we test during an annual inspection. But just to kind of show you, here's my piston wall right here. It goes in the cylinder, and you can see how much I can move it around. So when I compress the rings, now the piston can fit smoothly inside the cylinder. And I know you can't feel this, but you can kind of tell that that's really making a fair amount of compression. And I even have, or there's a lot of pressure there. And if I were to plug up all of the spark plug holes, you could probably actually hear the air go by. But if you can get a close-up there, you can see that the tolerance, the piston isn't riding on the walls of the cylinder, but it's very, very close to the walls of the cylinder. So this movement up and down of the suck, squeeze, bang, blow, that's what's causing our power. So I've got this piston removed again, and we've talked about what these 2 rings do. Those are compression rings. This 3rd ring is an oil ring. So that's the ring that's delivering oil to the walls of the cylinder. Now, we want gas and air on this side of the piston. We don't want oil up there. If we get oil on this side of the piston, it can foul up our spark plugs, right? Our best combustion is when we have a lot of gas and air, or the proper mixture of gas and air mixed, and we light the spark plugs and it explodes. If oil gets in there, it can cause a problem with that detonation process or that combustion process, and it also creates a lot of just oily mess up there, and it can foul up the spark plugs. So the job of this ring, this bottom ring here, is to scrape the oil off the sides of the cylinder as the piston goes up and down. So it makes sure that the cylinder walls are lubricated, but it also makes sure that they're not over lubricated. We don't want too much oil in there, because then we get oil blow by, and that can also cause oil consumption. So talking about failure modes again, if you're flying an airplane that is using a lot of oil, what could be happening is that these rings have actually lined up, and you've lost compression on that cylinder, and B, you're probably getting a lot of oil into the top of the piston, and that's where your oil is going. So you could have unexplained oil consumption where you don't see any visible oil leaks on the plane, you're just missing oil after the flight. It's probably because one of your pistons is burning oil, and that's how that could happen, is a failure of one of these rings. Now the piston itself is held onto the engine by the rod, and it's connected to the rod through this wrist pin. So if I take this wrist pin out, it fits pretty tight. There's my wrist pin. Now my piston is free here. Makes a great coaster. You could probably give it as a Mother's Day gift. but the wrist pin right here attaches to the rod. So this is my piston rod. And you notice the rod has a curved surface, and guess where it connects? Right here to our crank. So if you imagine as the piston is going up and down, piston's going up and down, the crank is moving in a circular motion. So that's what's happening inside the engine itself. So that spinning motion, our crank would be sitting in here, and our piston would fit onto the case just like this. So this probably looks a little more familiar, right? You can see where the piston fits on top of the case, and that spinning motion here, or this up and down motion here, translates to a spinning motion in our crank. So that's how the actual power transfer happens. So now that we've talked about how the up and down motion gets turned into the spinning motion, let's talk about how the combustion is actually happening, because these two things right here, these are our valves, and they're really, really important. You can see the valves are really just heavy-duty springs attached to these plungers. There's the inside of the view of the plunger there. So these valves opening and closing are critical to proper engine function, and these valve springs are pretty heavy duty. I'm able to compress them, but only if I really put my body weight into it. I would guess probably at least 50 or 60 pounds of force I'm having to push down to compress those valves. So those springs are pretty heavy duty. So how do we get those springs to move? Well, if you remember back to episode 1, the job of our camshaft is to move the lifter bodies up and down. So I've got a lifter body right here. So remember, these fit inside of the case right here. So I've got one of those removed. You can see on the other side of the case, this is where the lifter bodies sit, are back here. So these 4 holes are what lead to our push rods. So I've got a push rod right here. So this is the actual push rod, and this is what interfaces the lifter body right here to our rocker arm. So we have our lifter body, our push rod. At the end of this, we'll call it a valve train, we have our rocker arm. And notice how that fits on precisely like that. So this moves up and down, and our rocker arm moves up and down. And that up and down force is what compresses this valve and opens the valve. So if I can push down hard enough, I gotta put all my weight into it, but that rocker arm pushes down hard enough to compress that spring, which opens the valve. So this whole connection that I just showed you right here, you may have heard of this as being called the valve train. So think of train cars that are connected but able to move independently. That's our valve train. What is pretty incredible to me, I think, is that all of these things have holes in them and are able to transfer oil from our engine case all the way up our push rod into our rocker arm assembly, up to our valve assembly, and then that's allowed to drain back into our oil system. So this is actually the end of our closed loop oil system. Is the last place the oil drips out of the engine are these cylinder heads, and then drops back down into the oil pan and then starts the cycle all over again. So we have some pressurized oil up here in the top of our cylinders. And we have a lot of metal on metal contact up here, but not nearly as much movement as we have in our crank. So that's why I think losing oil pressure would affect your bottom end, your crank, before it would affect the moving parts at the top end of your cylinder. You just don't have as many moving parts. They're not moving as fast and not as much metal on metal contact as you have down here in your crank assembly. So this push rod here, you may not recognize it, but you actually look at it probably every time you do a pre-flight, and that's because it is located inside of this push rod tube. Now that push rod tube should be pretty familiar. You'll actually see it when we do our walk around of the actual engine, but that's the tube, the two tubes that sit on top of each cylinder. They just hold the push rod in there. Now, this push rod itself, when you're doing your pre-flight, if you see, and you can actually see here, this push rod tube has a dent in it. It's damaged. That's something that you would want to point out to a mechanic, because the push rod is in there going up and down like this. If this tube becomes bent and is making contact with the rod, then that rod is going to begin to fatigue. And if this rod breaks, guess what happens? Your valve doesn't open. Now the timing in your engine in that cylinder is all off, and you could have detonation, you could lose the cylinder entirely, or worst case, it could cause the rest of your engine to fail because it's detonating out of time with the rest of the engine. So if you see any damage to these push rod tubes, you want to address that to a mechanic and make sure that it's within tolerance. So a small ding like this, probably within tolerance, but you want to get an experienced mechanic's viewpoint on it. Fortunately, these push rod tubes are pretty easy to change out. In fact, that's true with their cylinders as a whole. A cylinder assembly could be pulled off and replaced with a new one in about a day, really less than a day. It's not a real big job. So these cylinders were actually built and engineered to be replaced, unlike the cylinders on your car, which are kind of built into the engine and can't be changed out independent of one another. The reason we do that is this is a high wear item. There's a lot of explosions that happen inside of this jug, and a lot of our heat from our engine occurs right here. This is where the combustion happens. So as hot as our crank could become, our cylinder head temperature is the hottest part of our engine. That's why we have a temperature sensor usually somewhere in this area that's measuring the cylinder head temperature, because that's where all the heat in our engine is occurring. Now, that's important that we remove that heat away, but it's also important that that heat exists, because that's the combustion that's creating the power for our engine. But I just find it interesting that out of a 200-pound engine or so that takes up a lot of space, really the only place where power is occurring is only about 6 inches in diameter and about 6 inches tall. There's not a lot of space where that combustion is happening. So if you look at displacement of an engine, that's what we're actually measuring, is how much air it can displace in each of the cylinders combined. All right, so that's my detailed explanation of the cylinder. Stay tuned for next episode. We're going to talk about the propeller and then how everything comes together. And we've got a couple of engines that are actually in operation on the Twin that we're going to look at, where you're going to see all these components and how they come together. And hopefully at the end of that, you'll have a much better conceptual understanding of how the engine works. So stay tuned for that. Thanks for watching. See you.